Hey, everybody. So I started on these experiments, and all of this research is because someone reached out to me. His name is Derek. He's a physics researcher, like very into theoretical physics, and especially into thermodynamics in a much deeper way than I am. But what he asked me to do, and what he basically said, is that look at and run experiments of the geometry and the thermodynamics between the layers of an LLM model. And then so that's what we're going to examine today. We're going to kind of be like kind of like brain surgeons a little bit, and we're going to dive into the brain of Bert. And we're going to look at the geometry and the thermodynamics of that and some interesting patterns that emerge from that. But before we dive into that, what I want you to very clearly understand is how exactly geometry and physics come into this equation. And it's very important to mention that very specifically, like geometry and physics are the two most disputed forms of like math and physics and science overall, right? Physics is less than 100 years old, or about 100 years old. Modern physics is less than 100 years old. Started in 1929, essentially, right? And then so within that, like all of our understanding of these subjects from that whole more holistic perspective, and it's not still not a holistic perspective, right? We still have gaps in it, but that mindset is less than 100 years old overall. And then within geometry, so like the kind of the major part of geometry is like Pythagorean theorem and everything surrounding that, right? So that whole part of geometry, like everything related to Pythagoras period, was like not accepted as into the full mathematical model until a few years ago. And then very simplistically, because it wasn't discovered until a few years ago that the Pythagorean theorem, so a squared plus b squared equals c squared, could be solved without the Pythagorean theorem, which was kind of a big milestone, right? Being able to prove Pythagorean theorem without Pythagorean theorem was important to prove that it's an actual like mathematical concept, and so they did that. But so all of the like bottom line is that all of this is very recent, right? And it's also very hard to, I realize it's very hard to understand and wrap your head around some of these things. And as I think of these things, I do realize that it actually comes up quite a lot in physics circles that I studied Deleuze, like Gilles Deleuze in postmodern philosophy, like quite extensively and for quite a few years. And Deleuzean theory, like to me, really helps ground these things and make me think about these things from a different perspective overall. And I think it's important to highlight that, right? Like Deleuze does a lot. It's hard, like Deleuze is hard for a lot of people to understand. It's another concept that's hard for people to understand, right? But to me, Deleuze is all about like relationships, spaces, and relationships and spaces, and that essentially, no matter what the space is, that the space is real, and that real relationships, which are just essentially like the physics concept of a relationship, right? An observer and an environment, and it doesn't have to be a conscious observer, right? Like conscious observer and observer are two different things. And then to me, conscious observer could be a human construct. Like it's not proven that it's not, but observer and environment is very provable, right? We can prove that 100% overall, like period. Without question. And then so within that, these two realms of science and mathematics are new, especially when it comes to like applying them to like matrix models and arrays and things like that, right? And then so kind of all of this does get into like new territory with regards towards the math, the physics, all of that. I think a lot of people don't understand that up front. But so I want to fully ground this concept up front that you should be treating these neural networks and the inside of a neural network actually like a physical place, right? And that's kind of the bottom line that I want to get through within this video. I want you to understand that geometry is related to spaces, and and the physics of that doesn't matter if the space is real or digital. It's related to geometry and not real or digital, right? Real or digital is a human construct. the geometry of a space is not a human construct. Is the space enclosed or not enclosed? Is it Euclidean space or hyperbolic space? That's question number one. Are there geometric objects within the space, etc., right? And then anytime that you put an observer into that space and that geometry, that's where interactions occur with the environment, and then that's where you get essentially effects of geometry and thermodynamics is what we're going to examine very specifically within this. And then so experiment number one, just to get your mind into the right place with this and understand that concept like fully in depth, I set up an experiment here where I'm utilizing agents in an environment, right? So this first test is utilizing swarm agents. And then very specifically, each swarm agent is designed and they start off predicting a probability of 0.5, every single one. So every single agent starts off in this category here, right? And then over time, what happens is they go into their environment, and then depending on where they are in their environment, there's different rewards, etc., right? It's like kind of like a big playground. And then so some will be biased to go towards one direction, and some will be biased to go towards another direction. What happens within that as far as our experiment? And then remember, again, 100% of these agents started at 0.5. And then so by 300 steps, we get a huge amount of diversity within this environment, right? And then we can see here's the complete breakdown of what happens within this environment. Here's all the code, and then here's how the agents evolve in this environment. And then literally the only thing that I'm programming within this that separates the agents is geometry, is the geometry of the environment. All of the agents start off 100% the same. And so I can't get that and stress that to you enough, right? So what is happening in this environment is that these agents are interacting with the geometry of the environment and then changing their behavior based off of the geometry of the environment very specifically, right? And then so some of them move, and we get a lot of diversity in this environment strictly through geometry of the environment, like no brute force coding. I don't have to tell these agents to do this. I'm not programming any genetics into the agents, nothing like that. It's all in the environment itself, right? And then the only thing that dictates this is where the initial placement and the random initial placement of the agent is, because it's not going to go far to start seeking rewards, right? And then they're based off of rewards, and then the rewards are scattered randomly throughout the environment. And so that's what's occurring, what we're seeing here. And then so now that we have an understanding of this as an actual physical space, I think we're in a good position now to dive into Bert's brain. And so this notebook explores the geometric and thermodynamic properties of Bert models during training and inference, focusing on attention mechanisms and feed-forward network activations. It investigates how these properties evolve with sequence length and training dynamics. So essentially, we're going to go through a few different concepts here, right? First of all, within geometry, we're going to focus on attention-based regimes. So we're going to analyze the attention mechanism by computing attention entropy and sparsity. And then we're going to utilize k-means clustering for this to identify distinct regimes or clusters based on these features. And I'll show you exactly what that looks like. We're going to project that into 2D space. Then we're going to utilize activation-based regimes. Kind of the bottom line here, we're going to look at this from an angle of geometry and thermodynamics very specifically, right? And then so geometry and dealing with entropy as well as sparsity is the two things that we're going to look at very specifically. And then we're going to look at a bunch of graphs and charts like this. And then so this is kind of like the shape of what happens within a model when you just give it you pass random information over its network. And that's what we're doing here in this particular instance, is I'm just passing random noise over the feed-forward network, all right? And then so we get here, but what we see very specifically by doing this is I'm able to get a scaling law fit for entropy within this particular model over sequences and over time. So essentially what I'm able to demonstrate here in this particular instance is that we have a thermodynamic scaling law that is present within the attention mechanism itself, right? This is measuring the attention mechanism of the model, and then we get a perfect fit to this scaling law, which essentially means that you're going back to, and I'm going to utilize this analogy in multiple parts of this, right? Because this is exactly how this breaks down. So transformers, you're prepaying compute, like you're putting your compute onto a credit card, right? And then you're doing that and utilizing the compute later. And then so within this, what these scaling laws are proving and showing out is like how much you have to have available in order to charge the credit card, right? And then in order to charge the credit card, it's not a one-to-one interaction. You're losing money on several different aspects of the model. So the first place that we're looking at within this is the attention mechanism itself, and then we're only focusing on the entropy of the attention mechanism in this first experiment. And already up front, we're gonna call it like 9 cents for every dollar. Okay, so for every $1 that you want to charge on the credit card, you need $1.09 available. And then that's just measuring entropy and just measuring the attention mechanism, right? And then so we go and then we look, let's dive deeper and further into this model, because I think probably a lot of people are still a little bit lost at this point. I mean, trying to make it make more sense for you, right? So in this instance, we'll measure both entropy and sparsity. So attention entropy and attention sparsity. So again, we're still focusing on the attention mechanism itself. And then so we're doing like, at this point, we're like taking apart Bert and then we're looking at individual parts of it. And then so right now we're looking at the attention mechanism, and then we're going to look at the individual layers. We're going to look at layer 0 and layer 6 specifically. And then we want to look at all three of these areas of Bert's brain kind of combined to get like the understanding of what exactly is going on inside of Bert here, basically. And then so we have in this instance, what we can do is I can fit out our both a sparsity scaling law, both a sparsity scaling law as well as an entropy scaling law. And then so what you can see here, and very specifically, this sparsity scaling law is like it's a worse payment than the entropy scaling law. Essentially, like you have a bigger penalty for sparsity than you do for entropy overall, is kind of like the bottom line that we see here. That's what this chart is showing here, right? And then so what we have here is, so our entropy scaling, we're charging like we'll call it like $1.09 for every time that we want to charge the credit card, and then also to every single, so it's $1.09 for $1, but then our sparsity penalty is another 17 or 18 cents. We'll call it our fee to Visa, right? Visa wants its cut, and then Visa is taking out another 18 cents out of our $1.09, and then so and then again we were only getting $1 out of that before, so then we put in $1.09, we get the dollar, and then Visa comes in on top of that and is taking 17.7 cents every single dollar as well, and then just boom, like and then this is just the attention mechanism, right? So again, pointing that out, and then so let's look at the individual layers within this, right? Because I've been pointing that out, that this is just the attention mechanism, etc. So let's look and apply this same type of logic across the layers. So in this instance, I'm going to utilize layer 0, so layer 1, layer 6, which is layer 7, and then layer 11, which is layer 12, right? So the total amount of layers within this particular network. And then what we can see, so layer 0, we have, here's our entropy and our sparsity numbers. So, and it's our sparsity scaling, and it's lining up perfectly with that. We go to, here's our full result for layer 0. Comparing to layer 6, we've got a completely different equation, right? So like layers, but so layer 6 changes our scaling law equations very significantly, which we were applying to the attention mechanism like in a vacuum, right? So within this, like our kind of where, like, depending on where we're at within the network, our dollar is worth even less, right? Our dollar is getting charged. So like if we want to essentially like hit layer 6, like we're getting charged a lot, like almost 50% interest just to hit layer 6, as opposed to if we're just trying to charge on the attention mechanism, right? But we have to charge all of these different aspects because like the transformer model is like all combined. We need every single aspect of it combined in order to prepay the compute, is kind of how it works. So we've now like, if the attention mechanism in a vacuum, we're prepaying, let's call it $1.09, and then 17 cents to Visa every time. And then if we want to but if we're doing that same calculation to layer 6, Visa's taken like all of our money basically. like they're taking like 60% of our money when it comes to layer 6. Is kind of how that kind of plays out, right? So like it beefs up, like we're paying more to hit here. And then once we get to layer 11, it gets worse, right? Like it's like we're like at this point, like if we want to like try to like directly pay into layer 11, basically, like it's like yeah, you can't. Basically, is like you'll lose money by trying to invest every dollar into like layer 11. Basically, is kind of what that proves out, and that's what that shows within our chart overall here, right? And then so what we see is that so now at this point we see that there's scaling laws related to both entropy and sparsity within the Bert model, and then that there's a small impact of that on the attention mechanism itself, and then so attention mechanism in a vacuum has a penalty, but then attention mechanism depending on the layer has a higher penalty, and then it increases throughout the layers, and then by layer 11 like you're losing money, like flat out, like you're like there's nothing you can do about that. You're bleeding off essentially. Like anything that you put into into layer 11, it's going straight into interest to the credit card basically. Like that's kind of how that breaks down to, right? And then so I want to now let's like visualize this, and then I want to run Bert through like actual tests, right? So we're gonna like train Bert through the like so we'll run it through like 5 epoch tests, and then we'll see if any of this changes, and then we're gonna also see like how Bert categorizes information overall, right? And then so that's what we do here. And then very importantly, this first test, notice it's 0% accuracy across the board, which comes out in kind of what this looks like, right? So this is the attention mechanism and how the attention mechanism is treating this data overall. So again, if we open up Bert's brain and we're just focusing on the attention layer itself, the attention layer seems to be able to separate this out. But then when we get into like kind of the attention layer across the different layers, the attention mechanism across the different layers, we can very much see it's not able to separate out these two clusters. It can't find a differentiation between these two clusters. So it can identify very specifically that there are two clusters, and again, the attention mechanism alone will, but when it's going through training for whatever, like so, in this instance, it could very possibly be setting up the model wrong in this instance on this particular data set, right? Just because of how it's performing within this. And then but that's a good test to know overall. And then we can also, that's verified by these metrics here, which are very far from 1, right? Which means that like the model's not grasping the shape. It's not understanding what is like the shape of the data set overall that we're trying to train it on. And then so let's kind of beef it up. And then so this is the data set that I'm training it on, right? So the blank sat on the mat, and then it should respond cat. A quick blank fox jumps over the dog, which it should be brown. And then so it's just, I'm masking certain parts of the sentence. And then we go through, and I'm able to I'm able to like improve the model dramatically in this instance. But what we can see here is, so like, first of all, pointing this out, and I should highlight this, right? So this is like what a healthy separation of the attention regime and separation looks like. You can see a lot more, we'll call it sparsity within this, right? Because there's a lot more separation between these as opposed to up here, right? A lot less separation, like a lot of overlap. Like we don't want that like overlap, and not having these separated is bad for the model, right? Because that means that the model's not actually distinguishing between these concepts, it's overlapping them, right? Whereas when we go here, like everything is spread out, and this is what we want. And then so these areas where it's like where we have like that little bit of overlap still, the model is, again, it's harder for the model to identify in those areas. The model wants to create sparsity in this space, so it wants like as much space in between all of these concepts as possible. And then when that happens, we get kind of, this is what goes on within Bert's brain with this, right? So this is translating here, and then we can see the geometry that takes place within here, and then very specifically the geometric shape of this data set in layer 6 is what we're looking at here. And then it's very, like, I want to highlight this very importantly, right? And then so you can 1,000,000%, if you figure out the right way to kind of like reverse engineer the process from here, get like this model, like this Bert model, to reconstruct this data set based off of just the shape that we're looking at here, right? You would train it on these shapes and then create its training program in such a way that it would be able to do that and detect these things and work in that fashion overall. So just highlighting that. And then what we can see here, just highlighting these numbers are well above 1, right? Whereas our numbers below were well below 1. So pointing that out, and then we get our accuracy of 1.0 here. And then this one we do further testing, and then this is an interesting one, right? Because this one is super interesting because the accuracy is low, but it's not 0. And then so you can see what happens. Like, so the model is able to like separate like a little bit, right? Like these kind of where you see that sparsity occurring. That's like the 0.07, 0.09%, right? Like very low accuracy, but you can see where it's accurately able to set, and then the rest is just like, I don't know, bro, like this is all just clustered in there, right? And then you can see it plays out here again in the geometry. It's so cluster 1 is just like everything that it can't identify, basically, and then cluster 0 is like what it's able to like separate out in this instance. And then in this instance, I start tracking the entropy across the layers as well. And then so what we can see very specifically is that we have scaling entropy, but not a scaling sparsity penalty when it comes to length, which is important, and it will play into this as well, right? So our entropy, like the amount of energy required to like in order to like compute this like this equation for the model rises dramatically depending on sequence length, as we're seeing here, right? So essentially, like the model is going to get more responses here, right, than it will here. But I'm going to point out why that is like bad overall in a later test. Like, it's like we want the like we're prepaying the credit card, right? And then so because we're prepaying the credit card and prepaying the compute, we want this equation to like, we want to prepay these equations as opposed to prepaying these equations. Like prepaying these, like we're charged every time that like we start the car, basically, and then so like every batch of the car, right, we're paying something on the credit card. And then so if we have a lower batch as opposed to a bigger batch, we can pay less here, but we see it scales actually more, right? So our length 10 has an entropy of 20.4, but then our length 30 has an entropy of 64.295. So again, it's scaling at 1.09. So it's scaling higher. Like we're paying more interest the longer sequence length that we have for the attention mechanism. Again, like our where it's, if our base price is $1.09, we also have to factor on the interest on top of it. So like it's getting like real, like Visa's just dinging us up at this point, right? It's kind of what I want to highlight within this. But so next experiment here, I want to show, and this one, I get the accuracy up a bit better. So I like this one because this is still low accuracy, right? Like it's ending at like, well, we get 100% accuracy in this, on this one. We end up with 100% accuracy, but the loss is different. And then we can see here how that works out with the separation that occurs within the layer regimes here. And then different, I mean, it's like interesting how like the model builds different geometries of these different data sets within here, but pointing out our scaling laws are holding true, right? So our entropy scaling is going up. So, and then not linearly, right? So 6.3, 10.1, and 13.7. And then in this instance, entropy, our sparsity does go up and start to go up as we feed actual real data into this. So we do have like a sparsity payment within this. And then what we're gonna see, and what I'll show you here, is that the models actually they like sparsity in the beginning, but not towards the end, is kind of the bottom line that we see come out within Bert's brain. Like the lower the layers. So if it's like layer 0, it likes sparsity at layer 0, but not so much at the later layers, like layer 6, layer 11. And then so here's this is the experiment where I wanted, where we have kind of the lower accuracy, right? So 0.35 to 0.26, and then we can see we don't have as much clear separation. So if we look at this as opposed to the one that was right above, this one, there's a massive difference, right? You can see that it's not able to fully cluster everything that it wants to or would be able to within this particular instance that we're looking at here. And then we have our entropy scaling going up, and then big loss and low accuracy. So pretty cool within that. And then I just run like multiple experiments within this just to highlight and showcase the different geometry and then the different layers. And then we can see that this, again, this geometry shifts between the different layers, right? So this is layer 6, and then so layer 6 of this geometry, and then what we're looking at, and then with these numbers, is different than when we looked at above with layer 0, right? And then so all of this combined hopefully gives you a good idea and a better concept as to like what exactly is going on within these models. It's not like voodoo magic. It's not anything like crazy out there, right? It's related to physics. It's all physics-based concepts, and then it like everything is bound by the laws of physics, even these models. And then so there's no free lunch. That's a part of physics as well. And then so like the bottom line, like there's limits and reasons why transformer models can't do like some of the things that people want them to do, and we have to look elsewhere for that within this. But like this hopefully gives you a good illustration of inside the mind of Bert, and like inside the geometric mind of Bert very specifically. If you like this type of content, please like and subscribe. Thank you very much.